Okay, so today we're going to start looking into factoring polynomials, whereas we'd factored quadratics before. Okay. The first thing that we're going to look at is just, are these things factored completely? Okay. We say that something's factored completely if it's written as a product of unfactorable polynomials with integer coefficients. So here, in my first example, 2 times x plus 1 times x minus 4. We've got it down to two binomials and the 2 on the outside. Is there anything inside of this that can be broken down anymore, that can be factored? No, there's not. So is this factored completely? Yes. Then I look at b. I have 3x times x squared minus 4. So 3x I can't break down anymore. Can I break down x squared minus 4? Yeah, I can. This is a difference of two squares. So this would be 3x times x plus 2, x minus 2. And then in the last example, 5x squared times x squared minus 3. 3 is not a perfect square, so we can't factor that anymore. So yes, this is completely factored. Okay, so the first step in any factoring problem is to find a common monomial factor. All that means is find something that all of these things share and divide it out. So x cubed plus 2x squared minus 15x. What's something that these all have in common? The x. So I'm going to take out an x. If you take an x away from x cubed, you're left with x squared plus 2x minus 15. Okay. And now I can check, can I factor this? Are there two numbers that multiply to negative 15 and add to 2?
5 and 3.
Yeah, so 5 and 3. So x plus 5 times x minus 3. Now I've completely factored it. In the next example, we have 2y to the 5th minus 18y cubed. So first I look at the numbers, the coefficients, and I see 2 and 18, they share a 2 in common. So I'm going to pull out a 2. And then I look at the variables, y to the 5th and y cubed. The highest power of y that they both have is y cubed. So I can pull y cubed out of each. So now, you just divide each of these things by 2y cubed. 2 divided by 2 is 1. Y to the 5th divided by y cubed leaves me with y squared. And then negative 18 divided by 2 is negative 9. And we took away all the y cubes. So now, y squared minus 9. Again, we have a difference of two squares. So it's 2y cubed times y plus 3 times y minus 3. Okay, in the last example, 4z to the 4th minus 16z cubed plus 16z squared. They all have a 4 in common, and they also have a z squared in common. So I can pull 4z squared out of everything. If I pull 4z squared out of 4z to the 4th, I'm left with z squared minus 4z plus 4. So now two numbers that multiply to positive 4 and add to negative 4. We have 4z squared times z minus 2 times z minus 2, so I can just say times z minus 2 squared. Okay, so we're about to talk about sums and differences of cubes. Before we go into that, let's get a good handle on our cubes. Okay, so a cube is anything multiplied by itself 3 times. So I'm just going to list out the first 10 cubes. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed, 64. 5 cubed is 125. And I'll list them all out, and you can just pick up the video in a second. Alright, so we completed the list that we can reference at any time. And we need to always be looking at this. because in our problems that we're about to see, we're going to see the cubes. Okay? And if we don't like have this list, if we need to find a cube root to know if it was a perfect cube, like let's say I was trying to find the cube root of 512. Well, I represent that by putting a little 3 out in front of the root. And to find this in a calculator, it's 512 raised to the 1/3. Okay, so this is how you can check if something's a perfect cube. Raised to the 1/3, we get 8. Just like what we saw over here, 8 cubed is 512. All right, we're going to look at some special factoring patterns. The first one is the sum of 2 cubes. And this pattern looks like this. If you have something represented as a cubed plus b cubed, that can factor down to a plus b times a squared minus ab plus b squared. So let's see what this looks like with actual numbers. All right. 8x cubed plus 27. Can I factor that down? Well, we can see this as a sum of 2 perfect cubes. Okay? Because 8x cubed is the same thing as 2x cubed. And 27 is the same thing as 3 cubed. Alright, so we went back to our table and we saw 8 and 27 are both perfect cubes. The cube root of 8 is 2. The cube root of x cubed is x. And the cube root of 27 is 3. Alright, so now that I can see that it's 2x cubed and 3 cubed, well, now this is of the same form as a cubed plus b cubed. So the most important thing that I'm doing right here is I'm identifying a and b. A is going to be 2x and b is 3. Okay, now that I've identified a and b, I'm going to plug them in to a plus b times a squared minus ab plus b squared. Okay, so that would be 2x plus 3 times, now I'm going to put this in an extra set of parentheses, 2x all being squared minus 2x times 3 plus 3 squared. Alright, so it's important to remember that all of a gets squared. So I end up with 2x plus 3 times 4x squared, because both the 2 and the x were squared, minus 2x times 3 is 6x plus 9. And that's my factored version. Alright, if we have 2 cubes that are being subtracted, like one from the other, a cubed minus b cubed, this is difference of cubes. And its pattern is a lot like sum of 2 cubes, but has 2 small differences. In the front we have a minus b, and now we have a squared plus ab plus b squared. So the difference between sum of cubes and difference of cubes, it switched this sign and this sign. Just this minus and this plus. Alright, let's see what this looks like. If I have 64x cubed minus 1. Okay, so just like any other time I check, is there anything I can factor out first? No, these two things don't have anything in common. So now I see that I have a binomial, because sum or difference of cubes will always be a binomial. And I check my list. Are both of these perfect cubes?
Yes.
Yes, they are. So I need to identify a and b.
4x.
So this is the same thing as 4x cubed minus 1 cubed. So a equals 4x and b equals 1. I'm going to plug them into the a minus b times a squared plus ab plus b squared. Remembering that all of a gets squared and all of b gets squared. So I have 4x minus 1 times 4x will be squared plus 4x times 1 plus 1 squared. So on the outside this stays 4x minus 1. 4x squared is 16x squared plus 4x times 1 is 4x and 1 squared is 1. Alright, 16z to the 5th minus 250z squared. First looking at the variable, they share a z squared. And then what number do they share? They're both divisible by 2. So now, inside the parentheses, I'm left with 8z cubed. Ooh, look at that z. 8z cubed minus 125. So I see a binomial with a cube. I check my chart. Are these both perfect cubes? So that way I can break it down. They are, right? So I'm going to identify a and b. So like a little side note over here, I go, okay, what cubed gave me 8z cubed? 2z. So I have 2z cubed minus 5 cubed. So a is 2z and b is 5. All of this, I have to go and look at, this is difference of cubes because there's a minus sign, so I know it's all going to go into a minus b times a squared plus ab plus b squared. Alright, so I'm going to start plugging all that in over here, back where we left off. Now, this 2z squared, it just has to stay on the outside. Okay. And then I have a minus b, so 2z minus 5 times a squared. 2z squared is 2z times 2z, that'd be 4z squared, plus a times b. What's 2z times 5? 10z. And then what's 5 squared for b squared? Plus 25. And then I'm done once I've plugged them in.